Hey everybody, this is Larry. This is me going over June 15th Leetcode Daily Challenge. So hit the like button, the subscribe button, join me on Discord. Let me know what you think about this problem. So you're going to hear the intro twice and probably skip forward a little bit. I'll put some timer markers on the end or in the video. But this is basically an intro to that problem or this problem because this is a long video. So, but this is long not because I didn't solve it. It is long because I really wanted to go into detail about how to solve this. And I solved this in two different ways, including learning that I missed an optimization that, I think it's interesting. It's long. Maybe watch it on 2x or skip ahead, like I said, using the YouTube button. But I do a little spoiler alert if you're here. I do go in detail about bitmask dynamic programming. So if you've been struggling with it, and I get a lot of requests about it, which is why I have this intro. If you struggle with it, please go there, go to that section, let me know what you think, and ask me questions. I can answer it either in the comments or next forum. Anyway, here's the actual video, so you can hear me do the intro again. Go. Hey everybody, this is Larry. This is June 15th. The middle of the June Leetcode Daily Challenge, the beginning of the third week. Hit the like button, hit the subscribe button, join me on Discord, and let me know what you think about today's problem. Match sticks to square. I usually solve these live, so it's a little bit slow. Fast forward. I try to give people a sense of what a realistic sense of how people actually solve this, and not just the perfect YouTube solution where the person pretends to know everything, or maybe they do, but still that's not the typical case. Anyway, today's problem is matchsticks to square. So you're given an integer with matchsticks. You want to use all the matchsticks to make one square. You should not break any stick, but you can link them up, and okay, each matchstick must use okay. So I mean, there are a couple of observations, and some of these you just have to kind of play around with in your head or with pen and paper, pencil and paper, until you get some of these. I think in general, I don't know if this. I never know if these things are hard or easy, to be honest. It's for me is either I know how to solve it or I don't know how to solve it, and everything I know how to solve is easy, and everything I don't know how to solve is hard. I guess that's how math and life goes sometimes. But ranting aside, there are a couple of observations, right? First is knowing that, okay, well, the sum obviously has to be if they're integers anyway, because you can, assuming everything's integer, assuming everything's an integer, then what was I going to say? Assuming everything's an integer, then the area has to be, or it's not the area, the perimeter has to be a multiple of 4. And then the next question is, how do you kind of break them up in 3 different pieces, right? Or 4 different pieces, sorry, but the last one being forced, I suppose. And there are obviously some shortcuts that you can do, like, okay, well, with one matchstick is too long, then but that's still not going to get you in a good case. Let's see. I was going to think. Just to kind of go. I mean, I think I know the answer, but I just want to go through it a little bit, which is that, I had a couple of thoughts about how to solve this. One is actually using dynamic programming with a sort of pseudo polynomial, kind of knapsacky kind of way, right? Because now we know the answer that we're going for, which is the perimeter divided by 4, right? If you have perimeter divided by 4, then you do some kind of knapsacky thing on the thing to see if you kind of get there, and that would get you the answer. Of course, that is pseudo polynomial, and for each matchstick is less than 10 to the 9, it's not going to cut it, because pseudo polynomial, it's the pseudo is very real. In this case, it's well, not real polynomial, it's just very big is what I'm trying to say. It was not a good joke, so the math purist, please forgive me. But yeah, so in this case, it's not going to be knapsack, because the perimeter is going to be on the order of 10 to the 9, which is too big to have a pseudo polynomial solution. But the thing that obviously the only other thing to notice, of course, is that matchstick is equal to 15. So that allows us to get a solution for sure. You think about how to construct it, right? I mean, the naive way of thinking about it, or one naive way of thinking about it, is that you know, if you think about having 4 boxes, or four kind of buckets, if you will, and then now you have 15 matchsticks, the optimal way to, or not the optimal, but if you brute force, what is that complexity, right? Well, it's going to be just 15 choose 4, right? Is that right? No, that's not right. What am I talking about? Sorry. A little bit late in the night. 4 to the 15, roughly. That's the number of total possibilities, but we can eliminate a lot of them. But that's going to be 4 to the 15. And of course, 4 to the 15 is 2 to the 30, which is, you know, a billion, right? So a billion is probably going to be too slow for this one, unless you have like a super computer. But Leetcode computer is not that super. So yeah. Then the second thing to note is that there is some sort of a state. And that is that, you know, whether each matchstick can only be used once, so we can kind of beginning to feel out a bit mass solution with respect to dynamic programming, and I think that's what we are going to do. The only other key part is trying to figure out. Okay, well, what is 15 choose 7? 15 choose 7. Sorry, just you plugging into my calculator. 6,435. Because that is the worst, maybe one of the worst case. Because okay, so another way of thinking about it is okay. So, and this is me without doing the, or this is me trying to do the math in my head. Of okay, so let's say I'm sketching out dynamic programming problem. I know that I usually explain these in a, and I will explain this in that way later. But usually I explain it in the way that I structure the code. Excuse me. Don't know what that was. But in any case, but I'm just trying to think about, okay, you know, I go over my thought process in depth a little bit, which is that, okay, let's say I have a bit mass dynamic programming, because 2 to the 15 is going to be fast enough, or not fast enough, but that's going to be few enough states, right? And then, so my idea is, okay, let's say I have some DP thing, we name it later, mask, and we know that, and maybe index, where maybe not index, maybe just sides. So so my rough idea is going to be sides as you go, and we'll go over it more in detail later. But I'm just going through my thought of conscience because I still haven't really solved it exactly. 3 meaning the number of sides that we finished. If and of course, if we're at 4 and all matchstick is used, we're good. And then the other one is mask, obviously, is just 2 to the 15 minus 1 bit mask for each item, and we'll go over what bit mask is in a second. I every time I do this, I get a lot of requests about bit masking. I'll go over it. Don't worry. I mean, it's not gonna be in super detail, but I'll go over it in enough detail, hopefully. Okay. So, but let's say this is our states, right? And this is where you know, and you plug in the number. This is going to be roughly, you know, this is 4, so this is going to be 2 to the 17. So what's 2 to the 17, right? 2 to the 17 is me pulling out a calculator just to double check it. So it's about 130,000. So that's like okay, right? So like roughly 130K maximum number of states. So as long as we do something that's inside fast enough, then that's going to be fast enough. So then the thing is, what do you do inside giving these states, right? Well, the way that we do inside, given that these states, is that what did I say 15 choose 7 is? 6,000. Is that fast enough? Maybe that isn't, but I have to think about it. But yeah, and we probably need a helper function to figure out so the way that I was thinking about it is that, okay, let's say we have a magic function, right? Magic function that let us pick k items from matchsticks that sums to n over 4, right? Or not n over 4, sorry, total over 4 or whatever, perimeter over 4. That's a better word. And then the question is, how do we generate this magic function, and do we need to cache it and something like that, right? I think that's probably the tricky part. Because now now we have to do some subset mask thing, which is a little bit harder as well, and it definitely adds to the complexity a great deal. If each of these will take maybe it's not that simple though, but these are the thoughts that I'm thinking about. Let me see if I notice anything else, because 15 factorial is a solution, but 15 factorial is obviously also very big. So then the question is, can we somehow do this magic function in a quicker way, or add another thing to the side? And just to kind of talk about it a little bit, a naive way of doing, a naive way of considering it would be kind of to have like a running sum, running total, or something like that here. But again, that is going to end up being pseudo polynomial, or maybe not pseudo polynomial, just straight up exponential. If, for example, if every item in matchstick is a power of 2, for example, then this is going to run for all 2 to the 15 or whatever it is. So then now your states are going to be 2 to the 15, right? So that's going to be too slow, or it doesn't help enough in either case. And that's why I made the comment about 15 choose 7, because that's the biggest number. And I wonder if that's going to be... The thing is that you have to be smart about it as well. Because you can't, like, in the worst case, you have a lot of... I wonder if there's some principle to kind of figure that out. How many count... I mean, yeah, I don't think there's any easy... I mean, it's... I wonder... so what I'm thinking now is whether there's an easy way to construct a list of all possible submask that does this, and do it in an efficient way. And and also in the worst case, right? I mean, you could do some early termination trick or whatever, but in the worst case, like for example, if all the numbers are the same except for 1 or something like that, then you're going to go for a lot of those duplicate cases. So we need to kind of figure out a way to prune it in a way such that this isn't dumb. And I don't know if this is a kind of a hard problem. So unless there's an observation that I didn't make, which is why I'm scanning back up again. So what I'm thinking right now is whether there is a dynamic programming solution that lets me, or something like that, but it's still kind of what we said earlier, right? It's going to be pseudo polynomial. So I don't know if there's anything easy with respect to that. Or by easy, I mean computationally easy, not like... maybe there's another definition, but that's basically what I'm thinking about right now. So yeah. Um, I wonder if there's something we can take advantage of with respect to the ordering, because I said initially that this is 4 to the 15, right? But of course that assumes some that assumes the sides are fungible or whatever. So that means that if you're able to kind of swap the boxes, how many are there? Well, I guess in that case, you just divide it by 4 factorial or something like that. So it's 4 to the 15 over 4 factorial, but I don't think that's going to be small enough. I'm again pulling out my calculator. 4 to the 15 is a billion, as we know, over 4 factorial. So that's 45 million. I guess that's actually maybe fast enough. Yeah, maybe I'm wrong on this one. And then the question is, how do I do it in a way such that I don't repeat states? I mean, because it's easy to say that we don't, swap out the things, but free form. I mean, I think the only thing, I feel like I'm feeling some probably about this as well is that so right now I have a branch and bound thing in my head. I'm trying to justify or reason the complexity, and that's the hard part sometimes with these recursive algorithms or like exhaustive search algorithms is that there are some obvious optimizations you can make, but you have to prove that they're fast enough, and I'm not so sure that I can. And the one that I have in my head is that if any sides is bigger than the perimeter over 4, then you obviously want to terminate early and just but I don't know if that's good enough, to be honest. We can actually let's play around with that idea, right? So basically you just have let's just say, because you have side 1, side 2, side 3, side 4. If I guess we don't even need it, we just need an array of sides. If any of if this is greater than, so the perimeter is going to be equal to the sum of the matchsticks. Oh yeah, so kind of skipping ahead a little bit or back a little bit. The reason why I'm trying this is because I just can't get the math to work with the dynamic programming. I did give it a good try, and that's what I was thinking about, but it's, but I just couldn't get it. So let's try this. Whoops. I always put parent on my bitwise operation. It's not a bitwise operation, I guess, but just because, I don't know, I feel like I never remember anything anymore. I'm getting old, friends. Okay. Otherwise, yes, we keep an index as well of which matchstick we're going to. Otherwise, if index is equal to n, then that means we used all of them. And if none of them are greater than the semi-parameter, then we just return true. So I think we're just good there. We could also check the sum of the sides, but that should be true if you used all the matchsticks, or if you're able to use all the matchsticks. So yeah. Yeah, okay. So now we try for each of the sides. Since we don't really need to know what matches what, we just return this. I think this is good. Well, this is good in implementation, but it may be too slow. So I have to play around with the constraints here. Because there are a couple of implicit things, right? One is that which I don't know if it's going to be fast enough, but one is that this branches a lot of possibilities, because as soon as it gets too big on one side, then it goes to the other. I don't know how to enumerate it in a good way or do the math. If you have any idea, leave a comment below. And then the other one is that we terminate early. That means that if we are able to find a solution, we return that is true as soon as possible, right? And what that means is that the longest case we're gonna face in terms of time complexity is one that is almost right but not right. So let's see if we can kind of construct an answer there. But let's also start by having at least these two test cases. So the really obvious case is just all the numbers are the same, which I guess is actually a force. And actually this is technically very quickly, because 15 is not divisible by 4, right? So yeah. So what is a number that's divisible by 4? So this should be good. This should return true, but maybe quickly, hopefully. So that's good. So now we want an answer that is So now we want to try to figure out an answer that is like our worst case is going to be an answer that the sum of the parameter is going to be divisible by 4, and there's no possible answer, and 15 elements ideally. How did I do that? I think it's just math, to be honest, but let's see. And all the elements are smaller. So yeah, that's also another thing that we can add, but I don't know if that's going to save us that much time. It's fine. Maybe it does. Let's do that, actually. But I don't know, to be honest. Well, this has to be a multiple of 4. So that means that if I want to change this one, this will have to be multiple of 4. Still true. I don't know how to construct. I mean, with more time, I can probably construct this one a little bit better. But let's give it a spin. Maybe it's time limit exceeded. Ooh, okay. So now we have that case that we were asking for. So let's take a look. I guess the taking a look is that it takes too long. Okay. But yeah, that was always one of my worries with respect to where to put it. Well, one more optimization that we can do is that we can actually sort by the largest value first, so that we always put the largest matchsticks first. Don't know if that saves it enough, though. Apparently it does, because the idea here is that I don't know if this is good enough to make it an AC, but let's give it a spin. The idea here is that the larger sticks will kind of trigger this thing earlier. Yeah, the idea there is that this thing will get triggered earlier, because so then you eliminate branches much earlier. I mean, this is accepted, but I don't know if I'm happy with this. Let's take a look at some hints. I don't know what the intended solution is, and I don't even know if I'm happy with this, like I said. So can we equal halves? Yeah. By the way, usually I'm not a English pedantic person. If you watch the stream, you know that I don't English very well anyway. But come on, 4 equal halves, halves, quads. Come on. Anyway, every match, well, I don't know which one. Try all the options. Okay. Particular size, we just need a length. I mean, that's basically what I did. Usually simply see the length of all sides of the equal. I mean, okay. That's just. So basically, this is what I did. Maybe it's better on Java, because I feel like this optimization is kind of neat, but I don't feel like, I mean, it doesn't, it's such a weird hack. And that's the thing, with, like I said earlier, with branch and bound or exhaustive search sometimes, with all these kind of optimizations, is that it's hard to prove the bound, because in the worst case, it's going to be still exponential, but you just hope that it is exponential in the way that the judge intended, which is kind of a crappy way of thinking about it. But which is crappy for competitive programming, but these kind of problems do come up more in real life, maybe not necessarily like, you know, back-end engineering or anything like that, but it does come up with respect to like just playing around with problems. But I would also say that in that case, it's more important to know the actual literature behind the problem you're solving, and usually it means knowing whether the problem is NP, right? If it's already NP or higher or whatever, or harder, I guess that's the more technical term. If the NP or harder, then you don't try to, you know, you try not to find the optimal solution unless you believe that P is equal to NP in polynomial time, and instead you try to find like an approximate solution in polynomial time or something like that. That's like one suggestion. There are other things you can do to play around within real life, but in real life, a lot of the times, well, depending on what you do, exactness is not needed per se. So that's why people have these approximation algorithms and stuff like that. But yeah, again, like, you know, I also think that maybe in another language this might not be needed, so I don't know. But let's spend a little. Okay, there is a solution. So let's see what the intended solution is, and see if they explain the complexity a little bit. Intuition. Yeah, I mean, okay, I know how to write recursion. Depth first search. Okay, so that is recursion. Like I said, it was 4 to the n and n. Okay. 4 to the n for n is equal to 15 should not be fast enough. It just so happens that, or I mean, it maybe is fast enough, but I cannot prove that it is fast enough. I guess that's my point. They also do the reverse sorting as well. See, like I said, this becomes a problem of it's a problem of guessing what the judge did, which is kind of weird, because on an actual interview, this is fine, because then you talk about, you know, you talk about thought process, you talk about the whys and the hows, even though it is a exponential complexity, you still talk, you know, they get to see how you attack a problem, even when there's no known solution. Let's do DP. What is the, this was a solution that I was trying to find. Okay, this is a very awkward one. Actually, this is the exact states that I had, but I couldn't prove this to be fast enough either. How did they prove this? Maybe I'll go over this one. Again, 4 equal halves. I was doing so I'm don't feel. So this is the solution that I had intended. If you watch the video through, this video is half an hour long, so I'm not gonna go over it today because it's just getting late. And that's where I said something about 15 choose 7, but I couldn't prove the Browns, which is why I didn't do it this way. Yeah, I mean, that part I knew. I mean, I think I said this as well. I mean, this is basically what I was saying. I mean, this is also this thing about where the 4 sides have been completely formed. That's actually what I was saying as well, because yeah. Oh. That is smart. I did miss this one. Okay, I think maybe I was too hasty. That is a wow. Okay, I'm not gonna lie. This is a clever optimization that I didn't think about. This is a medium. Well, that's a really sketchy way of. I mean, mind reading is always a little bit tough, but the DP optimization is actually like that is actually a very good solution. And I don't know if you're staying to the end. I hope you are, because I'm gonna do it the dynamic programming way. That is wow. 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 That is a great solution. I think that insight is probably enough to be making it hard. Yeah, wow. That is a great solution. Sorry, you're seeing my reaction live, and as a nerd, I get him when I see a good solution that I couldn't, not that I couldn't think about, because there are a lot of problems and solutions that I couldn't think about, but but when I see something that I was just like, wow, I'm in, like, it's kind of beautiful in a way, then I will point it out and I will get amused. So you're watching the amazement of Larry live, and I get a little giddy about it. I get a little happy about it, as you can see. Even happier than when I won that Leetcode contest, if you want to click on that below. But okay. So I understand the solution, because I was doing I did 90% of that solution, but I didn't see one observation or one optimization. I don't know about optimization or whatever, but that is a beautiful that is beautiful. So I'm going to explain that now and code it with you. So let's go over before what we said. I wish I didn't delete it. I don't think I could go back fast enough to kind of, like if I nope, I cannot undo long enough. So basically we have some states, right? So let's call it I don't know, can make. So we have an index and a mask, and this is the things that we talked about before. So index is O. Why did I say 0 to it? Oh, because before I said these were the number of sides made. So yes, this is sides, not index. Sorry, I have to use 0 to well, technically 4, but the 4 is, like by the time you get there, it's not quite the same. So yeah. So yeah. So let's just say this is four inputs, and then mask is 0 to 2 to the 15 minus 1. which is 2 to or 2 to the n, right? So this is 4 for the number of sides, and this is 2 to the n for the 4. Well, yeah, right. And then the key thing to note about this one is that, okay, so before we said if sides is equal to 4, then we return true. I think we said that before as well. And then the other thing is, because I was worried about that, before, and I'm just repeating what I said earlier. Let's say we have some magic function to enumerate things that make one side complete, right? So the idea is that I can have something like, okay, for each possibility in, I don't know, magic function, say, if the and this is obviously not real code, if the possibility and mask have no overlap, then we cache if can make sides plus 1, and then mask intersect, no, union, I guess, union possibility or something like that, right? Okay, and then we obviously, if this is true, we return true, otherwise we return false. Basically, this is what this is saying is that, let's say we have some magic function that gives us one side with the matchsticks that are used. Then we just kind of make sure that this has no overlap with, or basically, what this is saying is, if all the matchsticks in possibility is available, then you do this, right? Yeah, something like that. So that's basically it. But I couldn't figure out how to do this magic function in a reasonable time. But the one insight that I learned from reading that solution, and I'm very thankful that I did. I don't usually, you're watching the stream, I don't always do it. Sometimes I do it, but I don't always do it. But this is a good one. So I hope this is good. And yeah, so the key thing to note is that, okay, so now you have this bit mask, right? Now this bit mask represent, or you can translate this bit mask to the number, the bit mask translates to matchsticks used. And right here, if you already know what a bit mask is, fast forward. I'm going to give like a couple of minutes to explain what a bit mask is. And I promise you, bit mask, I know that sounds intimidating and there's all these O&1s and stuff like that, but I think the thing is that people overthink it too much. It's very simple. The way that I think about it is, okay, instead of using a bit mask, let's say we have a list of Boolean values, right? That's the entire thing. That's what a bit mask is. So what is a bit mask? So for example, instead of putting a binary number, you have a list of Boolean values, and that could be false, true, or something like that, right? Let's say that's the list that we're doing, and this corresponds to all the matchsticks, right? Like you have 1, 2, 3, 4, or something like that. I don't know. I'm just random numbers, but that means that false means that this is a used bit mask, say, yeah, right? And what that means is that. What that means is that, okay, false means that 1 is not used yet. This true means that this other 1 is used, and the 3 is used, and the 4 is used, right? So that's basically the idea. And then the other thing is, so what is a bit mask, right? Okay, we show a Boolean thing. So bit mask is just converting this into a binary number. For example, the false would be 0, the second false would be 0, the third digit would be 1, 0, 1, 1, right? And then now we convert it to a binary array. We can also further compress this into a number, because this is a binary number. So let's say this number goes to 001011, and then now this number is a bit mask. That's pretty much it. That's all bitmask is in concept. Of course, now you can see like crazy operations or whatever, but essentially there are only a couple of operations, and I'll go over over them as I do them. But for example, giving a boolean away, there are only a couple of things that you want to do, right? For example, you want to use sub index. So in bitmask, that's when you see, this is a little bit awkward. There is also a couple of ways of doing it. For example, you can, or something like that. There are a couple of ways of doing it. But just to give you an idea, if you see variations. But what that is saying is that, okay, let's say we have a boolean value, a boolean thingy. This gives you a 1 if that number is that digit, because 1 shifted by the index is just, like if we shifted 3 digits, oops, this will look like that, right? For example, so that's basically saying, okay, if this thing is a 1 and this thing is a 1, then the end of them, the bitwise end of them, will be a 1. And that's the only way that it can be a 1, and so forth. And then the other thing is use of index is equal to mask. Oops, oh, sorry. And the other thing is setting this is equal to true, which is just mask or 1. Right now, this video is really long, so I'm not going to go into it that much more. But you can prove it at home, right? Let's say we have set this is equal to false. Depending on how you do it, sometimes it's like this, assuming the bit is true, and so forth. There are a couple of things, and you can actually end it by the not version of this. For example, you can also do like something like that. There are a couple of ways to do it, like I said, but you just have to think through the bitwise operations and then just think about it. And then think about how to convert it from one to another, 1 bit at a time. And then it becomes, and obviously do some practice and it becomes more straightforward. So, okay. So yeah, so the bitmask translates to let's get back to the thing. The bitmask translates to the matchsticks used. So here, we... So this takes too long because the magic function, I just couldn't get something that runs fast enough. So now the thing is that the bitmatch translates to bit matchsticks used. And what does that mean? That means that there is a precondition or invariant in that the input will have sites completed and then the mask used, right? So then, but from that, you can calculate the current, because going back, right? Remember when I said something like, okay, sites, current, sum, mask? And I was like, okay, but I couldn't really figure out how to do this current sum in a way that is, that makes the dimension make sense, right? But it turns out that you can calculate this from this and the bit mask. So that's the part of the math the insight that I just couldn't get. And it's a hard one. And I hope, you think about it, and I hope I think about it in the future as well. But that optimization is enough to get it solved, I think. Because now you can do, okay, so extra side is equal to, okay, let's write some top things. Total of perimeter is equal to length for sum of match sticks. And let's do the 2 optimizations again. I should have maybe not deleted that, but yeah. So is equal to divided by 4 if perimeter mod 4 is not 0, return false. If any of x is greater than the x in matchsticks, false, right? So okay, so now we get the base stuff along the way. Okay, so now the extra side is just the total of x for x in matchsticks if 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 the mask and I have to do the enumerate. Right, and of course, just to rename this a little bit, let's call it used mask. So it's a bit mask to let us know what is used. And there's this thing. So one optimization that I'm already thinking about is that we can actually cache this. But for now, let's just let it be. Let it be. And you can also construct this with dynamic programming as well. So you can actually do it in faster time to do all of them at once. But this is going to be linear time, so it should be okay. In theory. So okay. So now we just go through the indexes one at a time. If used mask and one of index is greater than is equal to 0, meaning that it is not used. So like I said, the equivalent way of writing this would be if master index is not if this is not used, then that's basically what this code is writing. And so if this is not used, and extra side plus matchsticks of index is less than or equal to one side, right? So that's basically enforcing that this current side, or maybe current side is a better word. Current, yeah, okay. Also, I use different, using casing scenarios. So let's fix that. Okay. Then now we go, then if can make of sides. Oh, I guess we have to keep track of sides. Actually, do we even need sides? Oh, this is also modded by the perimeter. No, I missed that part. Because, do I even need sides now that I think about it? Because the sides is implicit. No, I think we have to keep track of it just in case. Okay. So if current side plus matchsticks of index is equal to the thingy, I mean, you can probably do some funkier one-liner, but I'm just going to write it out. If can make, let's just actually write it here. And can make of, no, let's do it here. Okay. If can make, the reason why I want to put it inside is the else statement later. Then we increment sides, and then we just use the used mask or one index, right? As we said, and this is just basically setting that index to true. Return true. We have an else here. Otherwise, if it is not, so it's just strictly smaller than, then we just do the same here. Except for without the side plus 1. And again, you can use some int magic on the boolean, but it's fine. And at the end, we return false. And that's pretty much it. So the key observation is just this thing that allows us to track current sum. This is a long video. I hope that you watch a good amount of it, because I spent a lot of time explaining. So it's not like, usually when it's long, I'm just not knowing what to do, but today that's different. So you start with 0 side and a 0 mask, because 0 means everything is unused, right? So this should be good enough, except for the memorization, because obviously this is exponential, like we said. Let's put this in. How do we retrieve previous solutions? Let's see. Oh no. Sorry, friends. Misclicking. I just wanted to get the case where I timed out, and that's how. I mean, I already know this. I mean, you know, we already read it, so. Yeah. Today I learned something. Or I revisited a good trick. So I like that. I like this trick. I mean, I don't know if it's a good. I mean, it's one that I have used before, but not quite like this. So I'm like I'm happy to see it and happy to learn it. But yeah. So yeah, we put it here. We'll see that it probably won't have time. Oh, that actually. How is that even fast enough? I didn't even cache. Wow, that is actually amazing. I mean, it's still slower than the other ones. I don't know if it's fast enough for all the cases, but that's already a lot faster, right? Because now, yeah, I guess it's just a lot faster. Well, okay. Wow. But yeah, but the additional thing that you can do, so take a look at that. It's 560, which my original solution couldn't even do. And we could still actually, we could still do the match. We could still do, use that optimization, because why not? Yeah, that optimization end up not doing that much. Interesting. Dun. Maybe it's just fluctuation in time. Let me just run it one more time real quick. Because, yeah, okay. Leetcode may be just being silly. But not the case. The next thing, of course, is noting that, as we usually do is with memorization, that all the possible inputs here will give you the same output. So let's cache it, right? Yeah. So and you know, writing your own cache is pretty straightforward. You just have force times 1/n. Yep. Cache is equal to, doesn't really matter because we're using. So this will create, and as we talked about, this is the number of states, 4 times 2 to the n, and this is what we did. And just to cache it, we go, okay, if has cache of sites used mask, return the cache, and then at the very end, well, not just at the very end. So this one is a little bit annoying, but we do know that is a singular. So let's just write has cache here. And then cache this as well. I don't know why I wrote 0 here. I think I'm just so used to that kind of problem. So yeah, so that's this part is a little bit annoying, but you just have to do it. And note that you may be tempted, and I have in the past, you may be tempted of, you know, writing if cache is true, return the cache value, but that means that you're not caching the false value. So that's kind of why I have 2 explicit things. So yeah, now it runs in 44 milliseconds, yay. So let's give it a submit. And it runs much faster, I hope. Let's see what that timing is. Oops, I closed it by accident. And we'll go over the complexity real quick as well, as soon as things load. Sorry, my computer/internet is slow. But yeah, so you can see that with the dynamic programming, this improved dramatically, right? With the branch and bound, which I wasn't even confident about, and we had to do some hacks to kind of get it right. So yeah, let's go over the complexity, which we can prove, right? So the number of possible inputs to can make, its size, which is from 0 to 3 effectively, because if it's 4, we just return true. And for mask, it's just 2 to the n, so this is going to be 4 times So the number of states is going to be 4 times 2 to the n possible inputs. So for space, it's going to be 2 to the n space. You just get rid of the 4 for constant. But for what's that one? For time, we do have a for n loop. So it's going to be, so each input takes O of n time, so total is O of n times 2 to the n. Yeah, that's all I have for this one. The trick that I couldn't find is this one, but 2 things. One is that, sometimes you just have to keep grinding, which I did not do. So I grind enough to have another solution that got accepted. Whether it's happy or not, you decide, but it got accepted, right? So sometimes you got to do your best, even if it's not, this is what I do. And then the second thing is just this observation, which I couldn't make, which is, it comes up maybe not once in a blue moon. It comes up but in a harder DP problems, this will come up, let's just say, not infrequently, say. So definitely you have to kind of think about these states. And in fact, in a lot of the harder DP problems, because the people are so good at DP problems and on a basic level, that is the problem. The problem is finding these states that you can reduce or prove to be, correlated to another or something like that, or just doing things in a different way, or implementation heavy or something like that. But yeah, that's all I have for this one. I hope that this part makes sense. I think I skipped over this one a little bit, to be honest. But basically, it's just, for the current side, you just add it if it's less than perimeter. If it's exactly to the perimeter, then we are able to make one more side. That's how we kind of go recursive that way. If not, then, we still have to build on the current side. But the key thing is only this one. I think to be honest, I think you can get rid of the side plus 1. I think it doesn't actually matter, because I think that doesn't do anything, to be honest, because everything is implicit or implied. So you can actually do that. It's just that as long as you have this, that should be good. So I might have an extra side here, but it doesn't really matter because it doesn't change the space and it doesn't change the time, so it's fine. But it doesn't change the big O of space, but I guess it does, it makes the space 4 times bigger, which may be needed for another one. So maybe that's another optimization that we talk about, similar to what we talked about. But yeah, this is a very long problem, or a long solution. I hope you go through it. Let me know what you think. This is a long video, but I hope this is very action-packed. So yeah, hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and so forth. Yeah, just come chill. And anyway, hope y'all have a good week. Hope you have a good day. Happy Tuesday. Stay good, stay healthy, to good mental health. And I will see you later. Bye-bye.